Hello, this is Richard Hammack's Calculus 1. We are in part 4 of the course on applications of derivatives. In lecture 37a, we'll talk about a new application of derivatives. We'll talk about how derivatives can be used to evaluate limits. We'll discuss a technique called LHopitals Rule. It's named after a French mathematician, pictured here, and as you can see, he had a very long name. We're just going to call him L'Hopital. He has the distinction of having written the first calculus textbook. He probably didn't invent the rule that we'll talk about today, but he wrote about it, and it forever bears his name. Here's our plan. Our goal, as I said, is to apply derivatives to the problem of computing limits. Think about a typical limit. We've looked at a lot of limits that look like the limit as x approaches c of f of x over g of x. And most often they have the form where the limit as x approaches c of f of x equals 0, so you're getting 0 on the top. And also the limit as x approaches c of g of x equals 0. So you're also getting a 0 on the bottom. And our usual strategy for evaluation of such limits is to try to cancel the terms that are creating the 0 over 0 and take it from there. Today we'll talk about what to do if this is not possible, if you can't cancel the terms. There are two topics we'll talk about. First of all, we'll talk about what are called indeterminate forms. And they are problematic expressions such as 0 over 0 that we're getting in this limit. And then we'll talk about L'Hopital's rule, which is a method for finding limits that have these indeterminate forms. Let's tackle the first item on the list, indeterminate forms. Here's a familiar limit. Limit as x goes to 0 of sine x over x, and we know that that equals 1. We developed that back in part 2 of the course. If you think about this limit, x is approaching 0, so on the top, sine of x is approaching sine of 0, which equals 0. And of course, the x on the bottom is approaching 0 as well. So we're getting 0 divided by 0 in this limit, but we know it equals 1. Here's another limit. Limit as x goes to 2 of 3 times the quantity x minus 2 divided by x minus 2. In this limit, the numerator is turning into 3 times 0, and the denominator is turning into 0 as well. So this limit also has the form 0 divided by 0, but it's easy to evaluate. You just cancel the x minus 2's, and you get an answer of 3. Each of these limits, we say, is a limit of form 0 over 0. In each one of them, the numerator and the denominator are both approaching 0. Consider this limit. Limit as x goes to infinity of 4x plus 2 over x plus 5. In this limit, the numerator is getting bigger and bigger and bigger and bigger as x goes to infinity, and so is the denominator, x plus 5. So we're getting infinity divided by infinity, but we know that this limit equals 4. You can multiply by 1 over x divided by 1 over x and apply those usual techniques, and you quickly get 4. So this limit has a form infinity over infinity, but the answer is 4. Here's another one. Think about the limit as x goes to 0 of 1 over x divided by 2 over x. The numerator, 1 over x, is approaching infinity as x goes to 0, either plus infinity or negative infinity, depending on which side of 0 x is approaching. And also on the denominator, the 2 over x is also approaching infinity or minus infinity, depending on whether x approaches 0 from the right or from the left. So this has the form infinity divided by infinity, just as this one did. But it's easy to evaluate this limit, this particular limit. You just reciprocate the bottom, multiply times the top, the x's cancel, and you get 1/2. So we have here two limits that have the form infinity over infinity, and we're getting different numbers. for these two limits. Each of these we call a limit of form infinity over infinity. So you can see from this example, when you have that form, you don't know what the answer is going to be until you work out the limit. Sometimes you think infinity divided by infinity should be 1, but that's not necessarily true. It was 4 in this limit and 1/2 in this one. These expressions, 0 over 0 and infinity over infinity, are called indeterminate forms. They're meaningless by themselves, but meaningful limits may have such forms, as we see here and here. So we have these two indeterminate forms, 0 over 0 and infinity over infinity. I should remark that there are other indeterminate forms as well. In lecture 37b, we'll talk about 0 times infinity and infinity minus infinity. And then in lecture 37c, we'll have 3 more. But don't worry about those right now. Today we're all about 0 over 0 and infinity over infinity. It turns out that there is a highly effective way of evaluating limits that have either of these two indeterminate forms, and it's called LHopitals Rule. And that's our next topic of discussion. Here's what it says. LHopitals Rule says that if the limit as x approaches c of f of x over g of x has indeterminate form 0 over 0 or infinity over infinity, then the limit as x approaches c of f of x over g of x, this limit we're interested in, actually equals the limit as x approaches c of f prime of x over g prime of x. And that's highly remarkable that these two things should be equal, but they are. And you can see the power of this because you know that in many cases when you take derivatives, functions simplify. So this limit might be a lot simpler than this one and easier to evaluate. There's a little bit of fine print here. I should point out that this works provided that the limit as x goes to c of f prime of x over g prime of x actually exists, but it's going to exist in like 99% of the cases you look at, so don't worry about that too much right now. I'll show you an example of LHopitals Rule in action. Think about the limit as x goes to 0 of sine x over x. And we remarked earlier that this limit has form 0 over 0. So this fits the hypothesis of LHopitals Rule. We have the limit as x approaches c of an f of x over g of x that has indeterminate form 0 over 0. And according to LHopitals Rule, it's going to be equal to the limit as x goes to c of the derivative of the top divided by the derivative of the bottom. Let's carry that out. So right here when I say LH under this equal sign, I mean we are applying LHopitals Rule going from here to here, going from this step to that one. According to LHopitals Rule, to work out this limit, you would take the limit as x goes to 0 in this case of the derivative of the top divided by the derivative of the bottom. So that's the limit as x goes to 0 of the derivative of sine of x divided by the derivative of x. And we get the limit as x goes to 0 of, let's see, the derivative of sine of x is cosine of x, and the derivative of x is 1. And this limit is very simple. You just plug in the x. You get cosine of 0 divided by 1, and cosine of 0 is 1, so we get 1. So there we have it. We just applied LHopitals Rule to evaluate this limit of indeterminate form 0 over 0, and we got the answer that we expected. It equals 1, but we did it with our new technique of LHopitals Rule. So again, here's LHopitals Rule, and we'll look at some more examples in just a moment. But first, I'd like to give you a quick informal justification of why we should believe LHopitals Rule, why this limit should equal this one. And let's concentrate on the indeterminate form 0 over 0. Let's say that the limit as x approaches c of f of x over g of x has form 0 over 0. So I want to show you that in that case, this limit equals this one. If we have form 0 over 0, this means that the limit as x approaches c of the top function equals 0, and also the limit as x approaches c of the bottom function equals 0. And just to make things simple, let's assume everything in sight is continuous. In particular, that means the limit as x goes to c of f of x equals f of c, if we're assuming f is continuous, and also the limit as x approaches c of g of x is equal to g of c. So f of c equals 0 and g of c equals 0. Now let's look at the limit as x approaches c of f of x over g of x. This limit, and we're going to work out why we should believe that it equals this limit. The first thing that we're going to do is we're going to change this limit slightly by replacing f of x with its linear approximation at c, which, if you think about a couple of lectures ago, is f of c plus f prime of c times x minus c. And remember, that's the equation of the tangent line to the graph of f of x at x equals c. It looks close up at c just like the graph of f of x. It's a straight line, whereas f of x is a curved line probably when you graph it. But when you zero in at x equals c, f of x is indistinguishable from f of c plus f prime of c times x minus c. And we'll do the same thing for the g of x on the bottom. We're going to replace that with its linear approximation at c. So on the bottom we have g of c plus g prime of c times x minus c. Now bear in mind here that the f of c and g of c that happen here and here, they're both equal to 0. So those two terms just drop out, and you're left with the limit as x goes to c of f prime of c times the quantity x minus c divided by g prime of c, that number, times the expression x minus c. And the x minus c's cancel, and we just get f prime of c divided by g prime of c. Now we're assuming that everything is continuous, so f prime of c is the limit as x approaches c of f prime of x, and likewise for g prime of c. So this limit equals the limit as x approaches c of f prime of x over g prime of x. So there we have it. The limit as x approaches c of f of x over g of x equals the limit as x approaches c of f prime of g of x, f prime of x over g prime of x. This equals that. Now you can shoot holes in this argument all day. For one thing, we assumed everything in sight was continuous, and you know that needn't be the case. You might have holes in the graph at c and so on. But this is just an informal justification to show you that these two expressions are expected to be equal. And if you're interested in a proof of this, or careful proof, you would do that in a course in advanced calculus, but we're not going to worry about this in Calculus 1. We're all about looking at examples of how to use L'Hopital's rule instead of why it's true. But this is why you would expect it to be true. Okay, let's look at some examples. First of all, consider the limit as x approaches 1 of 1 minus cosine of x minus 1 over x squared plus x minus 2. In this limit, x approaches 1, so the numerator approaches 1 minus cosine of 1 minus 1, which is 1 minus cosine of 0, or 1 minus 1, which is just 0, so we're getting 0 on the top. On the bottom, we get 1 squared plus 1 minus 2, and that's 0 as well. So this limit has form 0 over 0. So this is something that we can apply L'Hopital's rule to. So let's do it. And remember, when I say LH below an equal sign, I mean that in this step we are applying L'Hopital's rule. So according to L'Hopital's rule, this limit will be equal to the limit as x approaches 1 of the derivative of the top, which is sine of x minus 1, divided by the derivative of the bottom, which is 2x plus 1. So we get the limit as x approaches 1 of sine x minus 1 over 2x plus 1. And look at this limit. It's really simple. The denominator is no longer approaching 0. You can just use a limit law here and plug in x equals 1. You get sine of 1 minus 1 on top, or sine of 0. divided by 2 times 1 plus 1, and that's 0 over 3, so it equals 0. So we got a quick answer of 0 here using L'Hopital's rule. Now, if you think about the methods we had before we encountered L'Hopital's rule, what would you do with this limit? Maybe try to factor the bottom or cancel, or try to get rid of what was turning into 0, or use some trigonometric limit. It's not really clear how you would do that. You would spin your tires for a while, but look how quickly L'Hopital's rule gave us an answer. Here's another example. The limit as x approaches 0 of the square root of 1 plus x minus 1 minus x over 2 over x squared. So here, let's see, x is approaching 0, so you get the square root of 1 minus 0. That's 0 on top, and definitely 0 on the bottom. So again, this has form 0 over 0. So we can apply L'Hopital's rule to it. We get the limit as x approaches 0 of the derivative of the top divided by the derivative of the bottom. Let's see, the derivative of the bottom, derivative of x squared is just 2x, so there we go. For the top, you've got to use the generalized power rule here. This is 1 plus x to the power of 1/2. So when you do that, you get 1/2, 1 plus x to the power of minus 1/2 times the derivative of 1 plus x, which is just 1. And then the derivative of that 1 is 0, so that drops out. And then the derivative of x over 2 is 1/2. So now we have this limit by L'Hopital's rule. But if you look at this limit, it's not as nice as what we had before. X is going to 0, so that 2 times x on the bottom, it's turning into 0. And if you plug in an x up at the top, you get 1/2, 1 plus 0 to the power of minus 1/2, that's just 1/2, then minus 1/2. You're getting 0 over 0. So here we applied L'Hopital's rule, and we got another indeterminate form, 0 over 0. And this is going to happen sometimes. What you do in a situation like this is you apply L'Hopital's rule again, because once again we have a limit of indeterminate form 0 over 0. So you can use L'Hopital's rule to evaluate it. And let's see what we get. On the bottom, the derivative of the 2 times x is 2. Up at the top, the derivative of that 1/2 is 0, so that drops out. Then we've got to use the generalized power rule again. Bring down the negative 1/2 times the 1/2, that's negative 1/4, to the power of times x plus 1 to the power of negative 1/2 minus 1. That's minus 3/2. And, well, look at that limit. Just a 2 on the denominator. We're not getting 0 down below, and that's good. This is an easy limit to evaluate. You just plug in x equals 0, and in doing so, you get negative 1/4 times 1 to the power of minus 3/2, which is 1, divided by 2. That's negative 1/4 over 2, and that's equal to negative 1/8. So the moral of this example is that sometimes in applying L'Hopital's rule, once, you'll get another limit to which L'Hopital's rule applies. And you just apply L'Hopital's rule again. You may find that in some cases you apply L'Hopital's rule 2, 3, or 4 times before you get a simple limit that you can work out. Here's another one. Limit as x approaches pi over 2 of 2 plus secant x over 3 tangent x. Now, let's see. X goes to pi over 2. What's happening to the top? Secant x is approaching infinity. You have a vertical asymptote right there at pi over 2. So the numerator is approaching infinity. And likewise, the bottom, 3 times tangent x, that's approaching infinity as well. You have a vertical asymptote for tangent right at pi over 2. This limit has form infinity over infinity. But remember, L'Hopital's rule applies to the indeterminate form infinity over infinity just as it does to the form 0 over 0. So we can apply L'Hopital's rule here. We get the limit as x approaches pi over 2 of the derivative of the top, which is secant x tangent x, divided by the derivative of the bottom. Let's see, derivative of 3 tangent x is 3 secant squared x. Now looking at this limit, you can see that once again you're getting form infinity over infinity. So your first impulse might be apply L'Hopital's rule a second time. But wait a minute, let's see if we can simplify things before we do that. You've got a secant x over a secant squared x. So one of those is going to cancel. Simplify and we get the limit as x approaches pi over 2 of tangent x over 3 secant x. And that's still form infinity over infinity. But notice you can cancel some terms here. The tangent of x is sine x over cosine x. 3 secant x is 3 over cosine x. Reciprocate the bottom, multiply times the top. The cosine x's cancel. And we get the limit as x approaches pi over 2 of sine x over 3. That's all that's left when you simplify this fraction. And that's a really simple limit. The denominator is no longer turning into 0. You just plug in pi over 2 for sine of x. And sine of pi over 2 is 1. So this limit equals 1/3. So notice how in this limit, when we applied L'Hopital's rule, you got a messy expression, simplify. You might end up with something that's much simpler. And you can see that if you applied L'Hopital's rule to this one, as we did up here, that would just be a total mess. So as you're using L'Hopital's rule, simplify everything you can as you go along, and it'll make your life a lot easier. It's really important to work enough of these examples and exercises so that you get a feel for how this works. Some more examples, and these examples will involve the function e to the x. So off to the side, I've just reminded you of what the graph of e to the x looks like. It's always positive, and it gets big really fast. It approaches 0 as x goes to negative infinity. In this next example, let's look at the limit as x goes to infinity of e to the x over 1 plus e to the x. Now, x is going to infinity, and remember, as x goes to infinity, e to the x goes to infinity as well. So what are we getting? The numerator is approaching infinity, and so is the denominator. So this limit has form infinity over infinity. So L'Hopital's rule will apply to it. Applying L'Hopital's rule, we get the limit as x goes to infinity of the derivative of e to the x, which is just e to the x, divided by the derivative of 1 plus e to the x, which is just e to the x. Now, this new limit has form infinity over infinity, certainly, but it also simplifies dramatically. E to the x over itself is 1, so we get 1 for our answer. So again, we used L'Hopital's rule, we simplified, we got an answer. Here's another limit. The limit is x goes to infinity of e to the minus x over 1 plus e to the minus x. Almost the same as what we had before, but we have exponents of minus x rather than positive x. Now, as x goes to infinity, you get e to a negative number that's getting bigger and bigger. And remember, when that happens, e to the minus x is getting smaller and smaller and smaller. So e to the minus x is approaching 0 here and here. And what do we get? On top we get 0, and on the bottom we get 1. So this limit has form 0 over 1. Now watch out. That's not an indeterminate form. We have two indeterminate forms, 0 over 0, infinity over infinity, and this is neither. L'Hopital's rule does not apply in this case. In fact, we can just let x go to infinity on the top and get 0, and this e to the minus x on the bottom turns into 0 as well. So we get, working out this with the limit law, the limit of the top divided by the limit of the bottom is 0 over 1 plus 0, and that's 0. So be careful not to apply L'Hopital's rule to situations in which it doesn't apply. It didn't apply here. We didn't have an indeterminate form. And notice that if you had used L'Hopital's rule here, erroneously, you would get an answer of 1, which is incorrect. The value of this limit is 0. So pay careful attention to the forms that you have and don't use L'Hopital's rule blindly. Think about what you have. Here's another example. The limit as x goes to infinity of e to the minus x over 1 plus e to the x. Now here, just as before, that e to the minus x, as x gets bigger and bigger and bigger, that's a bigger and bigger negative number. That's approaching 0, whereas what's happening on the bottom, x is going to infinity, so e to the x is approaching infinity. This has form 0 over infinity. That's not an indeterminate form. Our two indeterminate forms are 0 over 0 and infinity over infinity. Those are the ones that L'Hopital's rule works for. This is not indeterminate, so we don't use L'Hopital's rule here. It doesn't apply. And in fact, this is one you can reason out. You could do this one way back in part 2 of the course. The numerator is approaching 0. It's getting really, really, really small, whereas the denominator is getting bigger and bigger and bigger, so you have a tinier and tinier number on top divided by a bigger and bigger number on the bottom, and that's 0. So again, be real careful not to apply L'Hopital's rule when it doesn't apply. In summary, we've learned L'Hopital's rule. And remember, it does have this caveat that it only works provided this limit exists. And I said for the most part, you don't have to worry about that. But I'll close with the warning that L'Hopital's rule may fail if the limit as x goes to c f prime of x over g prime of x doesn't exist. And I'll show you an example of that. This is our 7th example. Limit as x goes to infinity of x plus sine x over x. The bottom x is going to infinity, and on the top, x is going to infinity, and it's pushing x plus sine x to infinity as well. So this limit has form infinity over infinity. So we would expect to be able to use L'Hopital's rule on it. So let's give that a try. We get the limit as x goes to infinity of derivative of x plus sine x, which is 1 plus cosine x on the top. On the bottom, the derivative of x, which is 1. We get the limit as x goes to infinity of 1 plus cosine x. And think about that. As x goes to infinity, 1 plus cosine x, it's just oscillating up and down between 0 and 2, up and down forever. It's not converging to any single number. This limit doesn't exist. So we attempted to use L'Hopital's rule here, and it didn't give us an answer. L'Hopital's rule fails in this case. Every once in a while, that's going to happen. I want to point out that you can actually do this limit a different way that does work. Here's our second try. We have the limit as x goes to infinity of x plus sine x over x. We could tackle this by breaking up that fraction into a x over x plus sine x over x. And the x over x is 1. And as x goes to infinity, sine x divided by that bigger and bigger and bigger number x is shrinking to 0. So this limit equals 1 plus 0, which is 1. So our limit actually did exist, and it equaled 1, but L'Hopital's rule didn't give us an answer. It failed. Every once in a while that may happen, but like I said, when you're working the exercises, they're going to be of the type where this limit exists. But watch out for this. Maybe in Calc 2 or something, you might run into this case. That's it for today. Next up, we'll see there are more indeterminate forms than just 0 over 0 and infinity over infinity. In lecture 37b, we'll talk about indeterminate forms 0 times infinity and infinity minus infinity and how to handle them. I'll see you then, and goodbye.